This video is designed to be used as a pre-course assignment for the Soil Technology Measurement and Data Evaluation course conducted by the Natural Resources Conservation Service. It contains demonstrations and explanations of the use of 7 tools or methods for collection of soil data. These data will be used to populate databases, primarily the National Soil Information System database, commonly referred to as NRCS. This video also provides the student instruction in a format that can be easily reviewed as the need arises. For example, if the student is asked to provide data using the compliant cavity bulk density method, the student can use the tape to review the procedure used to gather this data. The 7 methods or tools to be reviewed are compact constant head permeameter, double ring infiltrometer, bulk density compliant cavity method, bulk density core method, EM soil electrical conductivity meter or EM38, ground penetrating radar, and aggregate stability field office method.
We're here today to talk about and to demonstrate a variety of measurement techniques for acquiring quantitative data for some of the common variables that we encounter to describe and to quantify water movement through soil or across landscapes. One of the most common challenges is to choose immediately and to think about carefully what it is that you're really after, because that will affect your site selection and where you are going to measure and what you're going to measure. We've chosen a site here in southeastern Nebraska that's representative of the typical landscapes and shows a variety of different land use activities, and any one of which can be chosen to base your measurements upon. For example, if you want to talk about and quantify or validate map unit content or design, you will find yourself placed in a different location on the landscape than you would if you were, saying, focusing on a particular cropping technique or a specific site investigation. If you want to look at the influence of map unit design, oftentimes you have to take into account breaks in slope or geomorphic position, and that will affect whether or not you're up on a ridgetop position, if you're here somewhere in the middle of a side slope, or whether you're downhill in a foot slope position. If you're after a particular site investigation, the boundaries are going to be determined by that particular application and may be irrespective of the map unit you're in. So site selection is a critical aspect of what you do. Choosing a site that's representative of your primary purpose is the foremost activity that you have to consider. Once having done that, you're in business to actually begin the process of opting between various measurement techniques and then pursue with the actual methodology of how you actually execute and acquire the data.
One of the field instruments used to measure in situ saturated hydraulic conductivity is the compact constant head permeameter, also known as the Amoozemeter. This tool will be demonstrated by Dr. Amoozemeter, Professor, North Carolina State University, Raleigh, North Carolina.
Today we are talking about measuring saturated hydraulic conductivity of the unsaturated zone or vadose zone. There are a number of techniques that can be used to measure in situ hydraulic conductivity. One of the techniques is referred to as constant head well permeameter method, shallow well pumping method, borehole permeameter method. These are all referred to the same technique, in which you dig a small diameter hole into the ground to the desired depth. You maintain a constant depth of water at the bottom of the hole, and you measure the steady state flow rate of water into the hole. And then based on the steady state flow rate of water, the depth of water in the hole, and the diameter of the hole, you calculate the saturated hydraulic conductivity, which is an index or a number that will define the rate of movement of water in the soil. So it's a measure of the ability of the soil to transmit water. The technique that I'm going to talk to you about specifically today is the constant head well permeameter method, and the device that will be used to maintain a constant depth of water at the bottom of the hole is referred to as the compact constant head permeameter that is available to you to make the measurement. To make the measurement, you need a minimum number of equipment. First, you need a set of auger. the best that we can use would be a 2-inch auger, and the reason that we use a 2-inch auger, which will give you about a 6 centimeter diameter hole, is that you don't need as much water as you use a larger diameter hole. This device has a 5-liter water capacity and can make measurement in most soils with one filling of the permeameter. Cleaner or hole cleaner or planer, and also you need a brush to brush the side of the auger hole that you've made in case that there is any smearing. The planer auger is used to square the bottom of the hole to form it into a cylinder. You also need a measuring tape or meter stick. You need a permeameter. You need water. Those are the basic parameter or equipment that you need. You also have to have data sheet that you need to prepare beforehand, and you also need to have your manual handy in case that you need to refer to it if you have any problem with any of the device. I'm going to explain the compact constant head permeameter here. This device is made of 5 parts. That these parts I will explain to you so you know what the system function, how it operates, and then you can work with it better and easier. The first part of these, there are 4 constant head tubes that are referred to. These constant head tubes, each one is capable of providing 50 centimeters of vacuum or negative pressure for you. Inside 3 of these are constant head tubes. They are fixed air tubes that are fixed and they do not move. And one of these constant head tubes has an air tube that is adjustable. That is that you can move it in and out. Before you start your measurement, you want to put some Vaseline or some vacuum grease on this tube so it can move up and down very easily. And we will later explain how you set these up when you are actually doing the run. So these are the 4 constant head tubes. In the middle, you have a 4-liter capacity reservoir that's referred to as main reservoir. Next to it, you have the flow measuring reservoir, which has 1-liter capacity, and there is a meter stick next to it that you can use that meter stick to measure the water level in the flow measuring reservoir. Then you have a water dissipating unit, that this unit will go to the bottom of the hole. There is a ring at the bottom of the hole, so when it sits at the bottom of the hole, it would not block any of the surface area at the bottom of the hole. And this is referred to as the water dissipating unit, and you have, in this case, you have about 2.5 meters of flexible plastic tubing that will assist you with putting the unit down at the bottom of the hole. And then finally, the last part of this is the base with a 3-way valve, and this 3-way valve has 3 positions. At the positions that you are seeing right now, the unit is connecting the main reservoir to the flow measuring reservoir here, and then when you put that one on the 2 on position, you're connecting the main unit to the flow measuring reservoir to the water dissipating unit, and when it's on 1 position, you have the flow measuring reservoir connected to the water dissipating unit.
After you've chosen a representative site, the next step is to clear an area of any unnecessary debris or obstruction so that you're prepared to clearly and cleanly auger a hole to the desired depth. I'd like to add a comment here. With these small diameter augers, it's often helpful to take very small bite-sized bits rather than to try to fill the auger completely, because they tend to jam up with soil material and makes it difficult to extract it. So it's far simpler just to simply take 1 or 2 turns, take it in small bite-sized pieces rather than go at trying to fill the entire auger. You want to collect the last bucket full of soil material and set it aside in a sealed container for soil moisture determination. Soil moisture content can affect the conductivity of the soil, or at least there's the potential for it, and so we're trying to collect that information along with the actual KSAT measurements. When you've bored your hole to the desired depth and have verified your placement, there's a couple of fine adjustments that need to be made. If there's a question about the location or the shape of the hole, one has a flat-bottomed planer auger whose purpose is simply to shape the bottom of the hole into a perfect cylinder. The objective here is not that, when one is augering, is not to compact the bottom of the hole, but merely to seat the planer auger lightly on the bottom and rotate it a few times so that it may simply shape the bottom hole. You're not attempting to dig any greater depth. When you're done shaping the hole, if there's concern about smearing of the sidewalls due to moisture content or the type of clay in the soil, you can use an optional brush attachment to simply insert it and to lightly scuff the sidewalls a time or two to minimize the smearing. The main horizonation at this site consists of a darkened AP horizon which overlies a series of BT layers. By augering or by boring a pilot hole, you can assess the actual horizonation and layering sequence at your specific site, and this will help you account for microsite variability. Once you've targeted a specific layer that you want to measure the KSAT for, you can then focus on determining what the midpoint is for the main horizon or layer you want to measure, and then determining the associated depth. That depth is the bottom of the borehole that you want to auger into the ground. At this particular site, we want to measure the conductivity, the saturated hydraulic conductivity of a lower BT horizon. So our borehole, the maximum depth of the borehole is approximately 80 centimeters.
Before we make the measurement, we make sure that we have water in the 4 constant head tubes. There's a water level mark on the constant head tubes, that you fill the whole of the tubes with the water to that level that is marked on the tubes. And then from the top port of the main reservoir, which is a large port in here, you can fill the 2 tubes together, making sure that the valve is on off position. That is, these tube and these tubes are connected with one another. After we fill the permeameter with water, we bring the permeameter, set it up next to the hole, and we'll just put it in here so we can use the level in here as a reference level for measuring the depth of the hole. The reference level for the permeameter is the top of this coupling tube that is in here. So we have to measure from the top of this tube down to the bottom of the hole. This is about 9 centimeters above the base in here, and we make measurement of the depth of the hole from the bottom of the hole to the top in here. That is 82 centimeters, and that will give you 91 centimeters from the bottom of the hole to the reference level on the reservoir. Then we have to set the constant head tubes so it will give us the water level that would be at about 76 centimeters, which is 15 centimeter depth of the water at the bottom of the hole. So we need to use 2 of these tubes. The second tube is fixed, and the first tube, we need to move this air tube from here. So it is approximately 25 centimeters below the bottom of the, below the top of the water in here. So the distance from the bottom of this tube to the top of the water in here would be approximately 25 centimeters. 25 centimeters and 50 centimeters, that will give us a total of 75 centimeters depth vacuum. For this tube system to function, air has to get to the top of this tube in here. For that, air goes through this tube in here, it bubbles, comes up in here, goes through the second reservoir, and there is a quick connect. So I connect the first one to the second one. Air goes to the bottom of this tube and then comes on top, and from the top has to go to the flow measuring reservoir, goes through the air tube in here, air bubbles up in here. We also connect the top of the 2 reservoirs together so the air pressure on top here and on top here will be equal. After the system is set up, we are ready to make the measurement. For that, we have to fill this tube with water so there will be no air entrapped in it. For that purpose, you hold the water dissipating unit up with all the tubes in it and change the valve from the off position to 2 on position. That would allow the water to come from these tubes. Make sure that the air on top is open, so the top you have atmospheric pressure right now. And the water comes out of this tube, and what you do is that eventually you're going to remove all the air out of it. You do not want to let this one to come too fast because you may bring air bubbles in here, and air bubbles will cause problem. Then you lay it down on the ground and let some water to go out of it and close the valve. Now we are ready to put the tube back in the hole, but before we do that, I'd like to just mention that it's always better to push this tube a little bit further down and make sure that all the tubes are connected with one another before you put this tube at the bottom. Then you put the tube at the bottom quickly and turn it out to the 2 on position. We'll see that the water has started going out of in here, and now air is coming from the top in here into this tube. It goes, bubble comes up, goes to the next tube, it bubbles from the second tube, it comes back to the bottom in here, and the air is coming in here, and water is going out of the tube in here. At that stage, you let the bubbling go until the bubbling becomes more stable, and as the bubbling becomes more stable and perhaps will be a little bit slower, then you know that you have reached the head that you have at the bottom. You measure the head then, and you go and do any adjustment that you like to have. As I mentioned, we like to start with the lower head in there. Rather than having 15 centimeters, we will have 10 or 12, and then we can always increase it to 15 centimeters or higher. I have to also mention that you do not need to have exactly 15 centimeters water at the bottom of the hole. You can have 15, 16, all the way to 30 centimeters of water at the bottom of the hole. However, you need to measure exactly how much water you have at the bottom, and that's what we do after the permeameter has come into an equilibrium. And right now we see that the bubbling has slowed down quite a bit, so we have established the constant head that we want at the bottom of the hole. There are a number of ways that you can measure the depth of water at the bottom of the hole. One way is to stick a rod or a wooden dowel or a meter stick, if you have it, all the way to the bottom of the hole, and then bring it out, see where the water mark is. But make sure that if you are doing that, use the thinnest and the smallest diameter rod that you have, because you are not going to raise the water level that much. The other option is that if you remember, the bottom of the hole to this level here was 82 centimeters. So if I want to have 15 centimeters, that means that the water level to the top of this base in here, we want it to be 67 centimeters. So anything around 67 centimeters will do it. So what I will do is that basically I insert the meter stick or my meter measuring tape here and bring it to 67 centimeters there, and then I bring it out. If I haven't touched any water in here, that means the water level is below this level in here. So what I will do is that I very slowly pass the 67, and I will go to somewhere like 75 centimeters in here and bring it out to see how much water we have. We have very little bottom at the bottom of the hole, so what I have to do is that raise this one another 5 or 6 centimeters and let more water go into the hole, and that way we start increasing the water level to the depth that we want. Once the water level reaches 15 or 16 centimeters, we measure that water level exactly. We determine exactly what depth of water level we have. We put it in our data sheet, and then we are ready to go. We'll let the permeameter run for a period of time, depending on the soil texture, the time that you have on your hand, and how fast the steady state is going to reach. The time may vary from 10 or 15 minutes all the way to maybe a couple of hours. Generally speaking, if you have time, you want to let this one go to come to steady state, so you don't have to sit here and babysit this unit in here, but you can always sit in here and keep making measurements. So we'll let this one go. Now it's becoming more stable. I'll go back again and measure the depth of water in here again and see how much water we have in the hole and raise that level accordingly. So it seems that we have to raise this one maybe a few more centimeters in there until the water level reaches the depth that we want. You notice that any time that I remove move this tube up in here. I'm raising the water level at the bottom of the hole. The unit starts bubbling for a period of time, and then it will slow down. And once the bubbling becomes more uniform in here, I probably am getting there to have 15 centimeters. So I have at the bottom of the hole right now 16 centimeters of water, because once I put this meter down in there, I have the 1 centimeter bottom in here that gets wet. So 67 minus 1, 66 centimeter from here. That means that I have 16 centimeter depth of water at the bottom of the hole. Now all I have to do is wait until a steady state is reached. And for that purpose, I'll go ahead and make measurements in here. And right now you can use a stopwatch, or you can use your own watch and determine, what the depth of the water will be here. As an alternative, what we can do is that instead of directly going in here and making measurement of the meter stick in here, some people like to use a tape, a removable tape, not masking tape, not any other tape that will stick to the tube. There are removable tape that you can buy from scientific supply stores, and you can use that tape and put it on the side of the tube, and you can make all your marks on it, and then you have to remove that tape and put it in your data book. And now all we have to do is wait until a steady state is reached. Generally speaking, you keep making measurements until 3 consecutive measurements are the same. Once we reach that level, we assume that we have reached a steady state level. Now, here we have the unit on 2-on position. That means that both reservoirs are connected to the water dissipating unit. Every centimeter drop in here in this tube corresponds with 105 milliliters or cubic centimeters of water going out. So basically what we measure in here per unit time, we multiply by the 105, and that is in your data sheet, and that will give you the quantity of water that has gone out per unit of time. You choose the unit of time that you want to use for measurements. It's best to fix the time and make the measurements, so you don't need to do any calculation. All you have to do is measure these distances, and if 3 distances in a fixed period of time, 3 consecutive ones are the same, you assume that you have reached a steady state. Now, if you are in a soil that the conductivity is not high, then what you need to do when you have reached a steady state, or you think you have reached a steady state, put the valve, rather than being on 2-on position, put it on 1-on position, so you only will get water out of this other tube in here. And this other tube, every centimeter drop corresponds to 20 milliliters or 20 cubic centimeters of water. So you can fine-tune your measurements. Another option that you have is increase the length of the time. Rather than making measurement every 10 minutes or every 15 minutes, you may want to make measurement every hour. But that means that you have to run the system for 3 hours to get 3 consecutive ones. So you put it in the other tubes and you can make measurements, and perhaps within 45 minutes after the steady state is reached, you can have the number of the data that you want in order to do the appropriate calculations. With this permeameter, you can make measurements from the soil surface, that is the water level would be at the soil surface, all the way to 2 meters depth. If there is any need to go beyond 2 meters depth, you can go to 4 meters depth by using a set of constant head tubes that would be in addition to the 4 that you have in here. So using another 4 constant head tubes, you can go to 4 meters depth. For that purpose, again, you take the top and set it on the side in here, and you fill the water to the water level that you have indicated in here is there, and then you make sure that these are all tightly attached to one another. And depending again on the depth of the hole and the depth of the water that you want inside the hole, and from the top of the water level to the reference level, you connect the appropriate number of these. And each one of these, as I mentioned, will give you 50 centimeters. Then you can put this one to the side, attach it, and connect these tubes appropriately in a series, and then the final one will go to the flow measuring reservoir here to achieve the number of constant head tubes that you need to get to the depth that you desire beyond 2 meters depth.
An example of a completed data sheet is included at the end of this section in your student training manual, which you received with this video. There are also exercises containing problems which you are expected to have completed before you attend the training session. Infiltration is the rate at which water enters the soil. In comparison to saturated hydraulic conductivity, infiltration is affected by properties of the immediate surface, including crust, biopores, and cracks. The double-ring infiltrometer is a tool used to measure the infiltration rate. The measurement is strongly affected by soil use and may change through the year. Infiltration is measured under conditions where free water is on the ground surface. After several hours, the soil profile becomes saturated to a depth of about 3 feet and the rate becomes fairly constant. This is referred to as the steady ponded infiltration rate.
Knowledge of infiltration is extremely important because it determines how much of the water that falls on the soil, how much of the precipitation actually gets in to the soil where it can be used. It's important for irrigation as it is for dryland agriculture. And the various models that have been developed for prediction of erosion for our agency all have estimates of infiltration, because it's the water that doesn't infiltrate, it's the water then that runs off from the soil that determines the, or is very important in determining the amount of erosion. And the method we have here is the classical approach that has been used for 75 years for measuring this so-called steady ponded infiltration rate. There's an aspect of the setup here that's very important, and that is how deep you insert the rings in the soil. I think you can visualize that in order to measure the infiltration rate, you need to have the rings down in the layer of the soil that limits the infiltration rate. And in this soil, that will be what we call the plow layer. And we'll want to insert these rings the order of 4 to 6 inches into the soil. I want to talk to you just a moment about the water source for the outer ring. You have water in this barrel, and in it you have a garden hose which is hooked to a float device, and this float device then will be mounted on the outer ring, and we will then be able to keep the water level in the outer ring at the level that we desire. And the water, I should mention, feeds by gravity from the water source here over to the outer ring. Here we insert the float on the outer ring, thusly, and now we're in position and ready to go. Now we're going to fill the inner ring with water, bringing it up to approximately the same level as in the outer ring. And just to recapitulate, the water in the outer ring is being controlled by this float valve that we talked about. And you see we've put an energy breaker there of straw because we don't want water impacting directly on the soil, because it'll cause dispersion perhaps. So we'll just pour this in. And I just checked very quickly the height of the water in there, and that's make sure that that's about the same as the level in the outer ring, and which it is. So now we're ready to attach the device for measuring now the rate at which the water moves into the soil from the inner ring, buffered, as you can see, by the envelope of water in the outer ring, which reduces and prevents lateral water flow. We want to talk to you now about measuring the rate of water movement out of the inner ring. And that is really what we're after here. You recall we have a float device that we use for metering the water into the outer ring, but that is really too crude an approach. And what we're going to be using here is a compact constant head permeameter. And here we have the water source from the permeameter. It's placed in the inner ring, as you see, and the bubbles now that you will see periodically in this device then mark the movement of water from the device to the inner ring to replace water that has moved out of the inner ring into the soil. So with this device we can keep the water level constant in the inner ring, and we're then getting a measure of how fast the water moves into the soil from the inner ring.
For a description of how to properly set up the compact constant head permeameter, please refer to the demonstration of the use of that instrument or to the instruction manual.
Now we want to initiate the measurement of the rate at which the water is moving out of the inner ring. And we do that by finding an even minute time here and marking this tape, as you see here. And then we will come back, and after a known time interval we'll mark it again, and we'll know the height of the distance between the two marks, and we know the diameter of the tube, and so we know how much water has moved from the inner tube into the soil in a given time. Now here we have almost 3 minutes elapsed, and when it has, we're going to mark this, and as you see here, and we now have right 3 minutes on there, so I won't forget. We now have the height of the column of water and the cross-sectional area, and we can get the volume of water that's moved into the soil in 3 minutes. And I think you could see from this that if you know the diameter of this tube and you know the diameter of the inner ring, that we then can calculate the infiltration rate, the inches per hour of water that has moved into the soil from the inner ring.
One of the methods used for measuring bulk density is the compliant cavity method. This method is designed to measure the bulk density of weak or loose soil material for which the clod or core methods are unsuitable. The method is particularly applicable to the near surface, including fragile tillage zones. It also may find application for deeper zones through sampling on top of horizons exposed in a soil pit. Zones as thin as 2 centimeters may be measured, and the immediate surface need not be disturbed. Bulk density is a very important measurement in soils and can be used to predict the rate at which water moves through the soil, the water-holding capacity of the soil, and the air-filled porosity of the soil.
We have here a wheat stubble, 2 rows of wheat, or at least they were wheat 3 or 4 months, or a couple of months ago. And this device is very simple. It consists of an annulus of sponge which is placed on the soil, and then a rigid annulus is placed over the sponge, and though not shown here, you drive in posts and mount this annulus on the sponge annulus on the soil surface. The size of the device is dictated by agricultural practice. Here you have about 8-inch rows, and so the device is designed so that you can then measure between 2 rows. It's very important in designing the device to have a scale that both permits you to make measurements of features and yet not lap over 2 or 3 interrows, so that you know what you're actually measuring. This is it's called a compliant cavity because you actually make a cavity on the soil surface which complies to the irregularities in the soil surface. Here's where we're going to make the actual measurement. We have the sponge annulus with the rigid annulus over it already mounted, and we're going to put in these threaded rods so we can mount the assembly on the soil surface. There are many ways to do this, but one thing you don't want to do is pound directly on the plastic. So you see what I'm doing here. I'm pressing it down so I don't pound the plastic. Then I make sure that the sponge annulus coincides then with the opening in the rigid annulus. So we're all done. We're all ready to, we've mounted the compliant cavity on the soil surface. And we use tough plastic film. This is about 1/2 mil diameter. And we have here a volume of water already metered out. It's 500 cc's in a graduated cylinder. And we pour that into here, into the cavity, and kind of seat it a little bit. Now this is a hook gauge. This is a bar with literally a hook gauge on it, which is just a hook that we can use to measure the water level. So we put that in the device, like so, if I can get it right. And now we have a situation where the tip of that hook gauge establishes a datum plane from which we can get the volume to the soil surface. We pour water in to exceed the level of the hook gauge, and then I take a 60 cc syringe and come in and remove the water until you just see the tip of the hook gauge breaking the surface. And then that water goes back in here. So now we have a measure of the dead space in the soil. And that volume is 500 cc's, which we started with. Now we have to take the water out of the compliant cavity, and you might save it if you hiked in a mile with your water into the woods, or otherwise you might throw it. You might throw the water away. Now we're going to excavate to the depth desired. I have a bag here and a lot of different tools depending on what you want to use for excavation. You need knives and spoons, and you'll soon gain experience as to the tools that are needed for your soil. Now, a very important point here, and distinguishes this method from most other methods, is that the depth to which we excavate is not arbitrary. It's determined by how the soil feels or the color. It's determined by the morphology of the soil. A second important point is that we can measure thin zones, a centimeter and a half or so, much thinner than we can do with the usual core procedure or the clod procedure. Now this is something you don't want to do. You got to remove the soil quantitatively. And we're going to go down about a centimeter and a half, and the reason we're going to stop there is because the soil feels firmer down there. So that suggests that there's another little bit that I got. I think maybe we'll just take a little more out. You see, in the usual core method, you might press in the core maybe 3 inches into the soil, and you may have gone through most of the really important changes that have occurred. Whereas with this method, you would not. You'd feel the differences. Now, the excavation should be a cylinder. It shouldn't be a little soup bowl. It should be a cylinder that is coincident then with the edge of this hole in the rigid plate, because we want the cross-sectional area of the hole to be constant. So again, try and don't make soup plates, make cylinders, and keep the excavation about the diameter of the rigid plate, or the hole in the rigid plate. So ordinarily then we would take this back to the office, and we would oven dry it. We would make a correction for rock fragments, probably, if there were, and then we'd have the weight. And to get the volume for the bulk density, which again is the ratio of the weight, the oven dry weight to the volume, we make a second measurement here of that volume, same way as for the first, and we use 1,000 cc graduate usually, because more water is involved. And here we're filling that graduate with the hole with the water from the 1,000 cc graduate. We put the hook gauge across. You remember I said that this is a datum plane, and the apparatus is so set up that you have to put the hook gauge in the same place each time. So what you're doing then is measuring the volume twice, and the difference between the second volume and the initial volume, which is the volume of the dead space, is the volume that you've excavated. And I'm going to go over here. Well, I have to add a little more water. I'm going to go over here and take this out and measure it. And we started with 1,000 cc, and we ended up with 280 cc's. So we have a net volume then of 720 cc's. And from that we have to subtract the dead space, which was 400 cc's. So we have a net volume of the hole of 320 cc's.
Another method used to collect bulk density measurements is the core method. The method demonstrated is a variation of other core methods in that the core does not have to be inserted to a specified depth. This increases the probability that soil compaction within the core will not distort the bulk density measurement.
We're going to talk here about a core method of bulk density, which we found very practical in the field under conditions where we can't get clods, and where the excavation compliant cavity method is inappropriate. We have here a small exposure, and the first step is to slice it down, get it flat. Yep. And of course, then in the process, you decide where you're going to make the measurement, and we're going to make it in just the lower part of the plow layer. We have here these cores. They're made of aluminum. They're sharpened a bit on one end. They're about 13 centimeters high and about 8 centimeters diameter. So we take the core and place it against the soil like this, and then you have to use a little muscle and come in and push this the depth that you want into the soil. What we can do, if really necessary, is tap it a little bit carefully. There you have to make a judgment whether you may be disturbing the soil too much. But we don't have to insert it a full distance. We can composite more than one core. That's a nice advantage to this procedure. Now we have to cut away the soil, and the objective is to get it broken out so there's excess soil at the bottom. So you can go something like so, and reach in and go like that. And there you have it. And now we'll cut it away. So we're square with the base of the core. Then get rid of the excess soil around the edge. And that's pretty good. And we can put it on a flat surface, and we know the volume of this core. But the question then is to get the volume of the soil inside. And there are several ways you can do this. One way that I do it is just take a ruler, and maybe I'll work it this way, and drop it, and then measure the height. There, it's 35.1. Maybe I should have to center this a little bit. And then the next one is 35, right on the button. And then the third one is 35.3. So then you write those numbers down, and I won't necessarily do it here. And then you turn it so that you can get another set of 3 numbers from the going the other way. This is 35, 35.2, and 35.3. And these little pieces of tape here are a ruler, so designed so that I keep the measuring tape more or less vertical when I'm making these measurements. Okay, so I know then, let's say it's 35 centimeters to the top of the soil, and then I know if that the total height from here to here is 37 centimeters. That is, it's this core height plus this bar that I have resting here plus 4 centimeters of this ruler here that's attached. So the difference between 37 and 35 is 2 centimeters. That's the average height of the soil. I know the cross-sectional area of the core, and so and that's about 40 square centimeters. So I multiply 40 square centimeters by 2 centimeters, and I get 80 cubic centimeters as the volume. And then I take the soil, and if I can find my bag, here we go. I transfer the soil and transfer it quantitatively now to the bag. sometimes, like in this soil, which is kind of wet, you gotta go in and maybe use your fingers even a little bit to get it all transferred. This is a soil with about 40% swelling type clays, and it sticks to everything. Well, now we've taken the sample, and we can take more than one and core and composite it if we wish. Once we go back to the laboratory with the sample, we have to oven dry it, and we have to make a correction for the weight and the volume of the rock fragments if there are any. And that gives us then the bulk density in grams per cc. You see, we have the weight in a known volume, and so the weight divided by the volume then is the bulk density. One major advantage of this procedure, and we've used it in a number of circumstances, is that it's something that can be done with simple equipment, and it is something that a person in a soil survey with rather rudimentary laboratory equipment can run.
Another tool for measuring the electrical conductivity of earthen materials is the EM38. The EM38 is a handheld instrument that has an effective observation depth of about 1.5 meters. It differs from the GPR unit demonstrated earlier in that it is self-contained and very portable.
Electrical magnetic measurements have been used in soil survey program to measure sinkholes in karst topography, as well as to measure the distribution and extent of sodium-affected soils. It has also been used to measure the depth of hardpan, as well as to measure soil quality. I will briefly explain how the instrument operates. At this end of the instrument is located a transmitter. The transmitter emits circular loops of electricity. The size of these loops is directly proportional to the electrical conductivity in the soil. At this end of the instrument is a receiver, which intercepts a portion of the current loops. The current loops that are intercepted are translated into an analog reading that can be measured using this meter. The measurements on this meter are directly proportional to the amount of electrical conductivity that is found in the soil. These dials and switches are used to set up the instrument. Electrical conductivity is read on this meter. The next dial is used to set the correct range depending upon the scale of the reading in the electrical conductivity meter. This dial turns the instrument off and on, and also is used to check the battery. These next two dials are used to set the IP0 or the in-phase null. The next dial is set at the factory and usually is not altered. This dial is used to set the QP0. It is a locking dial with the locking on this side. This toggle switch switches between QP and IP. During normal reading, the QP position is used. This button is used to transmit data to a data logger if it is connected. At the beginning of each measurement session, you must make sure that all metallic objects are removed from your pockets and hands, and that you are fairly far away from vehicles, fences, and power lines. There are several parts to zeroing or setting up the instrument. There's the in-phase nulling, setting the vertical and horizontal measurements, and finally nulling the in-phase measurement again. The battery is checked by turning this knob to bat and observing that the needle goes all the way to the top, indicating that the battery has sufficient voltage to make measurements. The IP switch is used for the in-phase nulling. This is done by changing this toggle switch to IP and adjusting the scale to this highest number, which is 1,000. These two knobs are used to zero the dial. First, adjust the coarse dial until the reading is near 0, and to make it exactly 0 by using the fine adjustment. This must be done for each one of the scale. So turn it to 300. Again, use the fine and the coarse to bring the needle to 0. Move this to 100, 0 the instrument again, and then move it to 30 for the final in-phase zeroing. The next step is to set the instrument so that the vertical mode equals 2 times the horizontal. This is done by switching the toggle switch to the QP position and then unlocking the QP0 and adjusting this knob so that the dial reads approximately halfway between 0 and 1, and then turning the instrument into the vertical mode and ensuring that it's at least twice that reading. If it is not, you must continue to adjust this dial until the vertical mode equals 2 times the horizontal mode, at which point you lock the dial. In order to set the instrument so that the horizontal reading is equal to twice the vertical, you must hold the instrument about 5 feet off the ground and then set the QP0 so that the scale reads about half the distance between the highest and lowest reading. And then turn the instrument vertically and check to see if that reading is twice the horizontal reading. If it is not, then you must turn the instrument in the horizontal position and decrease or increase the reading, and then check the vertical reading to see if it is twice the horizontal reading. You must continue to check vertical and horizontal until that relationship is true, that vertical equals 2 times the horizontal. The last step to setting up the instruments is to again check that the in-phase nulling is 0. We do this by placing the instrument on the ground, changing the toggle to IP, and then check to see that the meter reads 0. If it does not, we use the coarse or fine IP0 knobs and adjust them until the meter reads 0. And then we turn the meter into its horizontal position and check to see if it also reads 0. If it does not, we adjust this slightly so that it does. Now we're ready to make measurements. The last step to initialize the instrument is to again check that the in-phase nulling is set to 0. We do this by moving the toggle switch to IP, making sure the millimeter Siemens per meter knob is set to 0, and then we check the meter. If it is not 0, we adjust the coarse or fine 0 dials until the meter reads 0. Then we turn the instrument to its horizontal position. Again, check the meter to see if it reads 0, and make the slight adjustments until it does read 0. To make measurements, we turn the toggle switch back to the QP position. Now we're ready to make measurements. Try to understand how electrical conductivity measurements relate to soil properties.
Electromagnetic induction techniques measure the apparent conductivity of earthen materials. Though seldom diagnostic in themselves, lateral and vertical variations in apparent conductivity have been used to infer changes in soils and soil properties and to detect surface anomalies. One of the tools used to measure electrical conductivity is the ground-penetrating radar. The purpose of this video is not to show the viewer how to use ground-penetrating radar, but rather to introduce the principles and concepts of using and interpreting ground-penetrating radar.
The radar circuitry inside the ground unit generates a sequence of trigger pulses. These pulses are sent via the control cable to the antenna, where each trigger pulse is transformed into a bipolar transmit pulse. The transmit pulses are then directed into the subsurface by the antenna, which is pulled along the surface. The energy is radiated in a conical pattern, roughly 90 degrees front to back and 60 degrees side to side. The transmit pulse encounters different materials in the subsurface, each with different dielectric properties. Where the different subsurface materials meet or interface and the dielectric constant changes, some energy is reflected back to the subsurface and detected by the receiving antenna. The received signals are then sent back to the control unit where they are processed. The data are displayed on the color monitor and can be stored on the internal hard drive for later playback or printed on a thermal plotter. The horizontal axis on the display represents the distance along the ground surface. The vertical axis indicates the time it takes for the transmitted pulses to enter the ground, reflect from an interface, and return to the antenna receiver. This is called travel time and can be converted to depth once the velocity of the radar pulses is known. The strength of the return pulses determine the darkness or color on the display when in line scan format. How well ground-penetrating radar, or GPR, will solve a particular problem at a certain site mainly depends on two electrical properties of the subsurface materials: electrical conductivity and relative dielectric permittivity, or the dielectric constant. These properties are important to understand in order to acquire good data. Let's first look at the dielectric constant. This is a measure of the capacity of a material to store a charge when an electric field is applied. Different subsurface materials have different dielectric constants. The value of the dielectric constant ranges between 1 for air and 81 for water. You'll find a table in your SIR-2 manual that gives the approximate values for a variety of typical subsurface materials. At the subsurface interface, some part of the radar signal passes through the interface to the underlying material, while some is reflected back to the antenna. How much signal is reflected and how much passes through depends upon the difference of the dielectric constants between the two layers. In GPR, it is important that the change in the dielectric constant occurs over a short distance in order to produce a good reflection. If the dielectric constant changes gradually in the subsurface, reflections from the boundaries will be weak, discontinuous, or non-existent. For example, the ability to detect a water table is highly dependent upon the sharpness of the water boundary. A fine-grained sand layer could have steadily increasing water saturation with depth. In other words, no sharp water table boundary. This gradual change from dry to saturated sand is barely detectable. However, coarse-grained sands would have a sharp water table boundary, which would be easily detectable. The next property to understand is electrical conductivity, a measure of the ability of a material to conduct an electric current. This will determine the depth of penetration of the radar signal. The lower the conductivity of the materials, the deeper the radar signal can penetrate. Conductivity is controlled by the water, mineral, and clay content in the subsurface. The conductivity of water-saturated clay is high enough that it will greatly limit the penetration of the radar signal. Salt water is so highly conductive, it effectively blocks the radar signal from penetrating. On the other hand, dry sand, limestone, granite, asphalt, and concrete have low conductivity and allow good radar penetration. The chart in your manual also lists the electrical conductivity of typical subsurface materials. The depth of penetration is also dependent on the antenna selected. GSSI manufactures several antennas with ranges from 20 megahertz to 2.5 gigahertz. The lower the frequency, the greater the penetration depth, The higher the frequency, the better the resolution. Now, let's take a look at the process of conducting an actual survey. Before conducting any survey, you should first try to find out as much information as you possibly can about the site you'll be surveying.
The radar operator will need to know some of the following information: taxonomic family, geologic setting, terrain conditions, wooded, cropland, urban, size of the area to be covered, location of the site. The use of the terms you and your in the remainder of the GPR segment of this video refers to the radar operator. This section is included to give the viewer an overview of what is involved in conducting the survey.
So first we need to estimate target characteristics. Here are some questions to answer. How deep is the object that we want to see? What are the overall dimensions of the objects? What are the other subsurface materials surrounding the objects? How well are the boundaries of the objects defined? To illustrate the importance of knowing as much as possible about your target, there is a very general guideline that can sometimes be applied if you're looking for metal, cylindrical objects. The object should have about 1 inch of diameter for every foot of depth. So, you should be able to find a 3-inch metal pipe to a depth of about 3 feet. Beyond that, it would be increasingly difficult to see. If a pipe is at a 5-foot depth, it would need to be no less than about 5 inches in diameter to be visible. Remember, this is only for metal pipe. Other materials with different dielectric constants would have different requirements. And of course, the surrounding subsurface materials will also affect your data. The possible depths of your survey will decrease as the electrical conductivity of the subsurface material increases, the water content increases, the clay content increases, scattering of the radar signal increases, and conductive contaminants increase. Once your target characteristics are identified, you can select an antenna. The two main factors to consider are, first, what is the maximum target depth? And second, what is the size of the target? This difference in penetration depths and resolution makes selecting the proper size antenna crucial to the success of a GPR survey. The next step before surveying is to estimate the two-way slowness of the radar signal in the area we are working. At this point, the SIR-2 can be set up. If you'll be powering your system with a vehicle, as you see here, be sure the engine is running before you power the system up. Also, be sure you turn the system off before you turn the engine off. When the equipment is hooked up and the parameters set, conduct some preliminary test lines. The survey area should be gridded with flags, stakes, or paint placed at measured distances. The longer the test lines, the better. When surveying the ground, a minimum test line is about 30 feet. With a handheld antenna, make the line as long as is practical. It's also a good idea to do several test lines before doing the actual survey. When you're ready to do a test line, press the marker switch at the antenna to start data collection. Then double-click the marker switch when you start walking. If you're not using a survey wheel, try to pull the antenna at a constant speed, slightly slower than a normal walking pace. Press the marker switch once each time the center of the antenna passes the marked distances along the line. When you reach the end of the line, hold the marker switch down for 2 seconds to stop the data scrolling and close the file. If you know the location of some buried objects in the area, this is the time to use these targets to check the system settings and make necessary adjustments. Once you are satisfied with the settings, you can conduct the survey. You should try to not change the settings once you have started the survey. Again, remember to pull the antenna at a constant speed. Use the strain relief clips on the control cable and don't pull the antenna if the cable gets stuck. Never let the cable run underneath the antenna during the survey. It's best to have the cable drag behind the antenna as you pull it. Finally, Be sure to keep a detailed log of the survey and keep accurate notes of the files saved on your hard disk. You now know how to set up your SIR System 2 and how to conduct a survey. You're armed with a tremendous tool, and a key to your success is how well you interpret the data you acquire. In earlier sections of this training video, we covered the principles of subsurface interface radar. We touched on how the electrical characteristics of the soil affect wave propagation, types of soil where radar will be most useful, and how reflections from various interfaces occur. This will all be helpful in data interpretation. Let's now look at a basic ground-penetrating radar concept. Here, the radar pulses enter the subsurface and reflect off interfaces or targets. On the records we receive, the vertical axis is depth and time. Later, we'll learn how to convert this to feet or meters. Our horizontal axis is distance traveled by the antenna across the area of investigation. When interpreting radar data, you'll be considering three characteristics of the data. 1. How does the strength of the reflections vary? 2. Do the targets or zones of interest have unique reflection patterns? 3. What is the vertical and lateral extent of the unique patterns or reflections of interest? What determines reflection strength? Basically, the reflection strength is determined by the change in electrical characteristics between two layers, or the difference between a target and its surrounding medium. As we showed in the beginning, if water saturation occurs gradually with depth, you will not see a response from the water table. But if the change is abrupt, a sharp response will occur. This is also true in regard to changes in electrical characteristics. For example, a change from dry sand to loam represents a significant change in dielectric properties, from 4 for sand to 19 for loam. Let's review the following equation, where E sub 1 equals the dielectric of the first layer, E sub 2 equals the dielectric of the second layer, R equals the reflection coefficient. For our example of dry sand to loam, the equation looks like this. The reflection coefficient ranges from 0 to 1 and 0 to -1. The closer to 1 or -1, the stronger the reflection, and the closer to 0, the weaker the reflection. A reflection coefficient of 0 to plus or minus 0.2 is a weak response. Plus or minus 0.2 to plus or minus 0.35 is a medium response, and greater than plus or minus 0.35 is a strong response. Our example of dry sand to loam will produce a relatively strong signal response. Now, let's look at responses from targets. Let's consider a 6-inch diameter PVC pipe, air-filled, buried 4 feet deep in saturated sand. The dielectric of saturated sand is approximately 30, and the dielectric of air-filled PVC pipe is approximately 1. The equation now looks like this. Again, we receive a strong signal from this target because of the significant contrast in dielectric values. Here is a tougher situation. Let's examine what happens when a concrete pad is buried in dry sand. The dielectric of dry sand is approximately 4, and the concrete pad is approximately 6. In this scenario, the concrete pad would be virtually invisible. Understanding the dielectric values of the materials you're working with prior to starting a survey can help plan what to expect from your data. Let us divide interpretation into 3 general objectives and discuss what characteristic reflection patterns may exist. First, looking for man-made targets. Second, mapping the structure of the subsurface. Third, non-destructive evaluation of concrete structures. A cylindrical target, such as a pipe, tank, or drum, will produce a distinct response due to its shape. Thus, this is the first characteristic that we look for in the data. The strength of the hyperbolic reflection will depend upon the material as discussed above. Water-filled PVC or metal targets produce strong reflections. Air-filled PVC and concrete targets typically produce weaker reflections. When looking for utilities, you should expect to see the hyperbolic on several lines. In addition to observing the target reflections, you can also look for secondary features, in particular trenching. This often shows as a disruption in the horizontal subsurface layering. When interpreting natural stratigraphy, the continuity of reflections and their signal strength is an important consideration. For example, a wet clay underlying a dry sand will provide a large dielectric contrast and a strong reflection. In contrast, a silt overlying granite bedrock would not produce a strong reflection. If the pattern of continuity of reflectors change, we can interpret that as indicative of subsurface change. The water table will sometimes show as a strong reflection cutting across sediment reflections, while in fine-grained materials it will often not be observed. Air-filled voids in bedrocks have a strong dielectric contrast and thus produce strong reflections. Non-destructive evaluations of concrete structures normally focuses on one or more of the following objectives: location of reinforcing, determining thickness, and identifying various defects. Metal reinforcing bars show in the data as high-amplitude small hyperbolas in a regular pattern. Voids at the base of concrete, if large enough, will show as high-amplitude reflections due to the dielectric contrast. The reflections from the bottom of concrete can vary in strength depending on the underlying material. The reflection's continuity will vary depending upon the amount of metal reinforcing above. Once you have identified your targets or layers of interest, you'll want to determine their depth. Determining depth is an important capability of GPR. Depth is the vertical axis of the profile view. It is labeled in terms of time and can be converted to depth. There are 4 methods to estimate depth. The method used will depend on the required precision for depth measurements, available equipment, and site conditions. Method 1. Use assumed radar velocities from tables in your manual. Method 2. Locate object of known depth. Method 3. Geometric scaling. Method 4. Simple CDP. Methods 1 and 2 are the simplest and most commonly used methods. We'll discuss these 2 methods. Method 1, estimating velocity from the dielectric constant, requires that you know something about the materials that you're working with. If you can determine the dielectric of the materials, you can use this equation. Method 2, locate objects of known depth. Caution must be exercised because the velocity calculated is only an average to the target depth at that location. Lateral changes in moisture content of soil and rock composition will affect radar velocities. First, acquire a line of GPR data perpendicular to the long axis of a target of known depth, such as a tank or a pipe. Second, determine the travel time to the target from the GPR data. Third, estimate the velocity of the subsurface material using velocity equals travel time over depth. Fourth, the depth of unknown targets can now be estimated using depth equals travel time over velocity. You now understand how certain targets will be presented in your radar data, why reflection strengths vary, and how certain targets or interfaces can appear invisible to GPR, and finally, how to determine depth to a target or interface. Proceed cautiously. Never overinterpret your data. An anomaly is only an anomaly and becomes an identified feature only after proper ground truthing. Each situation you encounter will be slightly different. By now, you can see that used properly, the SIR System 2 is an extremely versatile and easy-to-use tool. Even though you now have all the basic information you need to conduct your own surveys, you'll find that every survey will become a learning experience. And the more you use your SIR 2, the more familiar you'll become with its wide-ranging potential for gathering invaluable data. Use it as much as you can and experiment with different settings in different environments.
The aggregate stability test is a method to determine the stability of soil aggregates under wetting and drying conditions associated with saturation by rainfall and subsequent drying of the soil surface. The procedure is based on visual observation rather than numerical measurement, does not require weighing, and takes very little distilled water. It is suitable for field office use and can be run on small samples such as are collected for correlation.
Here we are demonstrating an aggregate stability procedure that depends on the degree of reconstitution of aggregates when they're placed abruptly in distilled water. It has a big advantage in that you don't have to do any weighing. It's based on a visual assessment and placement of the soil into classes, which of course is not as quantitative as if you were going to weigh the soil material. But it's very well designed for the usual field office. Here we have a number 10 sieve, a 2 millimeter sieve, and a 1 millimeter sieve, number 18, and that's the base. We're going to put them together like so, with a smaller sieve below the upper. Here we have soil that was taken from the field and brought to the office and dried. And now we're going to take a part of it and pass it through this number 10 or 2 millimeter sieve and catch it on the 1 millimeter. And we use a heavy hammer here. This is one part of it that's kind of fun. You want to pass most of the soil material through the number 10 sieve. I think that's pretty good. I will take and we have the material retained on the 1 millimeter sieve here, and now we'll proceed to determine its aggregate stability. Now we have the 2 to 1 millimeter from the soil in the field that we're in. We have here a cell which has a 0.5 millimeter screen at the bottom, which will let the water in real rapidly, and we take some of this 2 to 1 millimeter aggregates, and we place the cell with the aggregates in them abruptly into this distilled water. The water rushes up past them, and effectively we have almost instantaneously immersed the aggregates in distilled water. We'll leave this overnight, and we'll take the cell out, drain it, and it'll be air dried, and then we will determine the degree of reconstitution and place that degree into a set of classes. Now here we have 2 cells. One contains a sample from native grass, long-term native grass, and the other from long-term cultivation, and actually the 2 sites are across the road from each other, and they would be mapped the same soil. They're not from the field that we're in. The reason we selected them is because we'll see a large difference in aggregate stability, quite a striking difference, and we wish to make a point. Okay, now I'm going to invert these. These would be, these samples then in the sequence of measurement would have been air dried, as we talked earlier, and now we're all ready to look at them. This is the from the long-term native grass, and this is from the cultivated field across the way. And you can see that there's been relatively little reconstitution. The sample, after being inundated in water, looks to be about what we started with, 2 to 1 millimeter discrete aggregates, whereas in this case we've formed a kind of a plate, and there's been considerable degree of reconstitution. Maybe I can just reach in here and open this up. And it may be hard to see, but this is almost devoid of any aggregate of aggregates. It's more like a mass. Now we take these two samples then, after we've performed the measurement we've discussed, and then we place them into classes. This would be a high class of aggregate stability, and this would be a low class. And we have a set of class definitions, in which we've tried to be as quantitative as we could, and though we have, as we've said earlier, it's a visual test, not a measurement. So there will be some variation in the placement made by one person versus another. And we ended up with 280 cc's, so we have